This video looks at another element regarding the boundary layer equations, specifically non-dimensionalization. And we want to specifically note that the boundary layer equations as we derive them, and as we'll be talking about today, are valid for laminar conditions. In particular, if we look at the boundary layer equations, we note that these are valid for steady flow or steady state. And that condition directly excludes turbulent flow, which we know is an unsteady condition. So under the conditions for laminar boundary layers, we've derived these three equations, one corresponding to the conservation of mass or volume, one corresponding to the conservation of momentum, and one corresponding to the conservation of thermal energy. And we can probably convince ourselves that for certain situations a solution exists to these three equations. And so if we were to define a specific situation, in this case I've tried to represent a flat surface where fluid is introduced at a certain velocity and with a certain temperature, and the surface is held at a certain temperature, then for some given location in this surface, we would expect that we could determine the velocity in x and y, as well as the local temperature based on these three equations. But if we move to a different surface that had a different length, perhaps had a different surface temperature, maybe a different flow velocity, free stream velocity, different free stream temperature, then we'd have to solve these equations again relative to these different boundary conditions. Or if I were to change the geometry, we would have different boundary conditions corresponding to that geometry. So what we're going to find, and what we're really looking for, is a much more general solution to this. Can we say something about these flows that look very similar? In both cases, I have a flat surface that I'm introducing a flow parallel to. Can we say anything general about both of these without having to solve the equation for the different boundary conditions? And we'll find that we can produce a very general solution to these equations by normalizing the variables, or non-dimensionalizing them. So for example, if we consider the position x in some coordinate system that we define for our region of interest, we can express the velocity and temperature at that position x and the corresponding position y. And that value we would expect to be different for this solution and this solution. Let's say in this case x corresponds to 4 centimeters from the leading edge of this plate, and in this case x corresponds to 40 centimeters from the leading edge of this plate. However, we might expect, given that these two geometries look so similar, that maybe there is a generalization we could make. In other words, rather than solving explicitly in terms of x and y, what if we were to solve in terms of the fraction of the distance or the fraction of the length of the plate? So in this case, our plate we said was 10 centimeters, so 4 centimeters would be 40%, or 4/10, or 0.4 of the length of the plate. And again, this would be 40 centimeters for a length of 100 centimeters, 1 meter. That again would be 40%. So maybe these two situations have some similarity based on the geometric similarity of these two cases, if we consider not the absolute value of x, but the relative value of x compared to the length of the plate. And so that's a fairly obvious non-dimensionalization for the spatial positions. And we're going to consider those non-dimensionalizations of the normalized variables with a star, an asterisk in superscript. And so we'll write x star as x over L, and we'll write y star as y over L. And then we can also do the same thing for all of the other relevant variables. So our equation here, we have two independent variables. or I should say two independent spatial variables, x and y. So we'll normalize them in that manner. And then we have the three dependent variables that we would want to solve for. And these are two velocities and one temperature. Well, the velocity we can likewise normalize relatively easily with respect to the free stream velocity. So we have a free stream velocity somewhere a long ways away upstream and away from our surface. So if we divide the velocity by that free stream velocity, we get a non-dimensional number. Again, all of the stars are non-dimensional. All of the variables with a star superscript are non-dimensional. That means that their units are they are unitless. They have no physical units. Likewise, we can consider a v star, velocity in the y direction, again normalized by the free stream velocity. And for temperature, we want to again divide by some relevant temperature or temperature difference. And so here, the obvious temperature difference to normalize by is the difference of temperature between the surface, Ts, and between the free stream, T infinity. And so if we consider T star as the ratio of two temperature differences, namely the temperature somewhere in the flow, T, minus the temperature of the surface divided by T infinity minus the temperature of surface, again we get a non-dimensional number for temperature. Now we have one more variable, and that's the pressure. Now this might be a little less obvious what we can non-dimensionalize with, but if we remember Bernoulli's equation and the relationship between static pressure in the flow, the velocity or the kinetic energy density of the flow, and the elevation of the flow or the hydrostatic head of the flow, then we get an idea that we can normalize against, again, a function of velocity, namely rho times u squared. So u, or u infinity, the free stream velocity, squared times rho tells us the kinetic energy density of the flow, and that has units of pressure, and it is a way that we can normalize the pressure, and specifically what we're interested in is the free stream pressure well away from the surface. But we remember our assumption that the pressure near the surface was the same as the pressure away from the surface at a given x condition. So using those normalizations, we can rewrite our boundary layer equations in terms of these non-dimensional variables. And so we'll start with the conservation of volume or conservation of mass, and this is relatively easy. We're just saying that the partial of u with respect to x plus the partial of v with respect to y is equal to 0. Again, we remember that we derived this by saying that the difference in inflow and outflow in the left and right and top and bottom faces have to equal 0 so that we conserve volume in the region of interest. And so we see we can express this in terms of our normalized or non-dimensionalized variables, essentially by multiplying both sides by L over u infinity. Again, if I considered this equation and multiplied by L over u infinity, then I can distribute u infinity into the numerator, or 1 over u infinity into the numerator and 1 over L into the denominator, and arrive at this equation. Well, of course, this side remains 0, and we can simply write the conservation of volume in non-dimensional form this way. So it looks essentially the same as it did in our dimensional case. Now, if we look at the momentum conservation equation, we can convince ourselves that we could rewrite this in terms of, or at least the advection terms, the advection of momentum in the x direction, in terms of the non-dimensionalized variables that we've previously defined. If we multiply this written in the non-dimensional form times u infinity squared over L, we convince ourselves that these two terms are equal. been a little bit more explicit in the term relating to the pressure gradient in the free stream. And we can say that if we were to divide the numerator, or divide P infinity by rho over U squared, then we have to multiply by rho over U squared in the numerator, this prefactor. Likewise, if we multiply by L in the denominator of this prefactor and divide X over L, then we change these into their non-dimensional forms and introduce this factor. And likewise, for the second derivative of U with respect to Y, then we get a prefactor to our second derivative of U star with respect to Y star of U infinity over L squared, analogous to what we did in this term. So if we just multiply through, or actually multiply the entire equation through by L over U squared, then we would arrive at this term. The rows cancel, U squared over L goes away here and here, and we're left with U over L in this last term. So we've simplified the equation somewhat, but more importantly, we've introduced a term that you're familiar with and probably have some association of its importance in terms of the physics of the flow. We have here the kinematic viscosity, nu, divided by the velocity times the length scale. Well, we recognize that as 1 over the Reynolds number. And I'm always going to write the Reynolds number, I always should write the Reynolds number with a subscript that tells me what length scale that I'm defining. So we remember from fluid mechanics, Reynolds number is velocity times a length scale over kinematic viscosity, or if I remember the definition of kinematic viscosity, I can write that as density times velocity times a length scale divided by dynamic viscosity. And we remember from fluid mechanics that the Reynolds number really tells us the ratio of the forces that are driven by inertia in a flow compared to the forces that are driven by friction, by damping, by viscosity in a flow. So just by looking at this equation, we know that there must be a solution that exists for the flow that we can express U star in terms in terms of a function that has as its arguments the non-dimensional positions, the Reynolds number, and this pressure gradient. Now the pressure gradient really is a function of the problem geometry. So if we were to fix the problem geometry, we know that this non-dimensionalized pressure gradient should remain the same if we fix the problem geometry and the boundary conditions for the problem, or at least the non-dimensionalized boundary conditions. And you use this frequently in fluid mechanics. Rather implicitly, you said that you knew what condition the flow was in if you knew the Reynolds number. In other words, if I were to pick a specific position, let's say somewhere in a pipe, then if I knew that I had a pipe of a given geometry, let's say it had a circular cross-section, and I knew the Reynolds number, the fact that I was given a pipe with a certain cross-section told me something about what dP star dx star was, and if I knew the Reynolds number, then you could tell me whether the flow was turbulent or laminar. It would say something about this solution for you. Although that's a little bit of an extension beyond what we specifically consider here, because all of these boundary layer equations are referring to the laminar case specifically. But what we want to really pay attention to is that if I know Reynolds number and I fix the problem geometry, and really that includes the type of boundary conditions that are applied to that geometry, what the boundary conditions look like, if not their absolute magnitude, then I am able to say what the flow looks like at any given non-dimensionalized position. And if I know what the velocity is, If I know what u star is, then I know what the velocity gradient is. If I know u star as a function of y star, then I can tell you what the gradient of u star with respect to y star is. And if I know that, then I can tell you what the gradient in u with respect to y is if I apply the definition of my non-dimensionalization. And from that, I can tell you what the surface shear stress is. So the surface shear stress tells me one of the key things that I want to know in a fluid dynamics problem, what the drag force is. How much frictional force does a flowing fluid apply to a surface that it's flowing over? And I can express that in terms of a friction coefficient. In fluid mechanics, you define this CF equal to the local shear stress divided by the dynamic pressure or the kinetic energy density of the fluid. And since we know u star is a function only of x star, y star, non-dimensional position, and Reynolds number, and this pressure gradient, which we can convince ourselves stays the same for defined problem geometry and set or type of boundary conditions, then for a specific geometry, in other words, let's say this is a sphere, then a sphere of any size, and as long as my assumption of a laminar boundary layer applied, then I can express the friction coefficient only as a function of the non-dimensional position where I am and the Reynolds number. And so if I know the Reynolds number, I know how much drag is applied to the flow. And let's also remind ourselves really quickly a physical interpretation of this term, or I'll show this term specifically in dimensional form. This looks very much like what we had derived in the heat equation, that the second derivative of something with respect to position expresses the rate of change of something stored in that region. I'm being very vague there because in the heat equation, this was the second derivative of t with respect to y or x. And this would have been k, and that would have told me how quickly heat was diffusing into or out of a region. In this case, I have the second derivative of u with respect to y times kinematic viscosity. This is telling me how quickly momentum is diffusing in or out of a system. And that's really what the drag is also saying something about. It's saying how quickly the flow is giving up momentum to the surface. So we start to kind of see the analogy with heat transfer. In heat transfer, we're interested in how quickly the flow is giving up or taking away energy from the surface, thermal energy. In this case, in the analogy to fluids, we can look at how quickly the flow is giving up or taking away momentum from the surface. And we can repeat the same sort of analogy for the equation of conservation of thermal energy. And I'm not going to do the algebra, I'm going to leave that to you, but if we make these non-dimensional substitutions or substitution for the non-dimensional terms that we've defined, and importantly, if we neglect the viscous dissipative heating. We remember in the thermal energy, the full thermal energy equation, there was another term that depended on viscosity and the square of the gradient of velocity. Well, we said that term corresponded to the conversion of mechanical energy into thermal energy via viscous heating. But that is usually negligible in most of the cases that we consider, in this class at least. And so we're gonna drop it. If we do that, then we end up with a fairly simple equation that actually, again, looks pretty similar to the one we looked at before. without that pressure gradient term. We have this advection term, the rate at which fluid flow is carrying thermal energy into or out of a region of interest. And then we have this diffusive term, and you recognize this term immediately from the heat transfer or the heat diffusion equation that says that the second derivative of T with respect to position, in this case non-dimensionalized, tells me how quickly heat is diffusing into or out of my region of interest. Now again, we're considering a laminar boundary layer for steady flow at steady state conditions, and so this rate of diffusion has to balance the rate of advection. So when we make this non-dimensionalization, if we work through the arithmetic, then we see that the prefactor for this diffusive term becomes alpha. Again, that's the thermal diffusivity, right, which is K over rho times C sub P, divided by U times L. Well, we can expand this term into two terms, and we can multiply by nu over nu, and have one term that's kinematic viscosity, nu over velocity times length scale. We recognize that from the equation we just considered as 1 over the Reynolds number, again, REL, L is our length scale. And this new term, alpha over nu, or thermal diffusivity over kinematic viscosity. But we remember what we were talking about on the last page, that this kinematic viscosity was related directly, or gave us a proportionality between the gradient in momentum and the momentum flux. And actually, let's flip back and take a quick look explicitly at that and remind ourselves that we had this diffusion term, and again, this is diffusion of momentum, and the constant that determines the rate at which momentum diffuses is kinematic viscosity. So if we compare that to the thermal energy equation, we have a thermal energy diffusivity, or thermal diffusivity, of alpha, and we have a momentum diffusivity of nu, or kinematic viscosity. So this ratio of alpha over nu is actually incorrectly written here. I'm going to correct that and properly write it as nu over alpha. So the Prandtl number gives me the ratio of the momentum diffusivity to the thermal diffusivity. So in analogy to what we considered before, for fluids, we were interested in the drag on a surface, or again, the rate at which the flow gave up momentum to a surface. In heat transfer, we're interested in the rate at which thermal energy is transferred to the surface or from the surface. And again, in fluid mechanics, we were able to relate that drag force to a gradient in velocity in fluid mechanics. At the surface, we have a no-slip condition. We can express the heat flux in terms of Fourier's law, the gradient in temperature at that surface, now times the thermal conductivity. And if we consider our non-dimensional definition of temperature and position y, then our gradient in temperature at the surface, y star equals 0, is equal to the non-dimensional gradient times T infinity minus Ts. Again, that's just from our definition of T star, times Kf over L. Again, over L comes from our definition of y star. So In heat transfer, we're generally, for convection, basically trying to come up with H. And the problems before, you were usually given H. That's what all the chapters ahead in convection are interested in finding, determining what H is. Well, if we know, if we're able to solve this equation in terms of T star, and we can then find what T star, the derivative of T star with respect to Y star is, then we can solve for H from this definition, the fact that H is heat flux divided by Ts minus T infinity, just by the definition of Newton's law of cooling. And we can relate then H to this temperature gradient at the surface. Again, there's no slip at the surface. So if we know the temperature gradient, then we know the rate at which heat is being conducted through that thin layer of material, and that tells us what the heat flux is. And we can express that in terms of T star with respect to Y star. Well, if we rearrange this equation from this definition, again, Newton's law of cooling tells me that heat flux is equal to H times the temperature difference between the surface and the free stream temperature. So from that definition and this relation from the non-dimensionalization, we can say that H is equal to K of the fluid. Again, importantly, this is the thermal conductivity through the layer of fluid divided by L times this non-dimensional gradient. Then if we express the non-dimensional gradient in terms of H and L and Kf, we'd say that it's equal to HL over Kf. And this is a new non-dimensional number that we've introduced that we're going to call the Nusselt number. And this we can think of as a non-dimensional or dimensionless, non-dimensionalized heat transfer coefficient. Really what it's telling us, we talked about this before, is I can break this into two pieces. I could say this is L over K F divided by 1 over H. And this really is two thermal resistances, right? This is the thermal resistance that I'm actually getting via convection. And this is the thermal resistance or a thermal resistance that I would get if I were just conducting through the fluid for a specific geometry. This L, I would have to come up with exactly what L meant. But I see that this is a thermal resistance of conduction through the fluid, and this is a thermal resistance of the actual convection. So what this is really telling me is how much better am I doing by stirring the fluid than just by conducting. So following the same logic as for the drag coefficient or friction coefficient for the solution of the momentum equation, we can probably convince ourselves that the solution of the thermal energy equation in terms of a gradient of temperature with respect to position, or non-dimensionalized temperature with respect to non-dimensionalized temperature, can be expressed in terms of the non-dimensional position and the Reynolds number and the Prandtl number. So with these two non-dimensional numbers, and an important thing to note for the Prandtl number is that this is a property of the fluid. Now, it does depend on the temperature, as each of these properties depend on temperature, but the momentum diffusivity, the kinematic viscosity, and the thermal diffusivity are both properties of a fluid that I can look up at a specific temperature. So the Prandtl number depends only on the fluid composition and essentially the temperature. The Prandtl number can also be affected by pressure for a gas, though for a liquid we would generally consider them to be incompressible. Now, one last important thing to note for this solution for the Nusselt number, or the non-dimensionalized heat transfer coefficient, is we can solve for this gradient at any point in the flow that we're interested in. So we express it specifically at the surface. By definition, we're looking at the surface. And so we consider the x position along the surface. In that case, the Nusselt number can vary by position along the surface. I can have one Nusselt number here and another Nusselt number here, which is not surprising. My boundary layer would be growing if my flow was moving in that direction. I would expect the heat transfer to be decreasing if this was at a constant temperature. And so likewise, I would expect my Nusselt number to change with position. However, frequently, we're interested in how the entire body behaves. And so then we would introduce what we talked about in the lecture last week, an average Nusselt number. We'll average the heat transfer coefficient along all positions in space, and then arrive at an average Nusselt number, which is the average heat transfer coefficient times our relevant length scale divided by the thermal conductivity of the fluid. And that, since we're integrating over all positions, is no longer going to be a function of position. It will only be a function of Reynolds number and Prandtl number. So if we know the Reynolds number for the flow and the Prandtl number for the fluid, and for a specific geometry, regardless of what its scale is, you can tell me what the heat transfer coefficient is via this relation for the Nusselt number. And I also want to point out that the Prandtl number has some more implications given this relationship between momentum diffusivity or momentum diffusion and thermal diffusion. So if we consider the boundary layer where the surface influences the flow, we know we have two different boundary layers that can be of different thicknesses depending on whether we're talking about a boundary layer in velocity or a boundary layer in temperature, a momentum boundary layer or a thermal boundary layer. And the relationship between these thicknesses is given by the Prandtl number. And physically this makes sense. For laminar flow, this will be the Prandtl number raised to some power n. And this makes sense given that we consider both of these to be diffusivities. Nu is telling us how fast momentum is diffusing to the surface, whereas thermal diffusivity is telling us how fast thermal energy or temperature is diffusing toward the surface. Really, thermal energy is diffusing toward the surface. So the Prandtl number encapsulates that important physical relationship between these two transport processes. One last thing I want to point out is table 6.2 in your book, and that gives us a list of dimensionless numbers and the physical interpretation. It's a very useful resource to look at. So we looked at the non-dimensionalization of the three boundary layer equations, and we pointed out before that once we non-dimensionalize them, they tend to look, the equations themselves look similar, specifically the momentum and the thermal energy equation. Particularly if we neglect this change in pressure, this pressure gradient, which for example, for a flow of a flat plate in parallel flow, this is explicitly zero. The free stream pressure is unaffected far enough away from the surface of the plate. So if we can neglect this term, then these two equations look essentially the same, just a difference in this prefactor. If we were to replace U star with T star, these equations are the same. We've just changed this constant value in front of the diffusion term. And that leads us to the suggestion that the solutions to these equations should look the same. And that further allows us to imply that there should be a relationship between the behavior of the transport at the surface for momentum and for heat. Again, we said nu was kinematic viscosity was talking about the diffusion of momentum, whereas the thermal diffusivity was the diffusion of heat. And so if these solutions look the same, then we ought to be able to express some relationship between the diffusion of momentum or force and the diffusion of heat. And explicitly, we can write this similarity in the solutions as an equivalence between the drag coefficient times the Reynolds number over 2 and the Nusselt number. So practically, what does this mean? It means if we know the drag for a specific body, we can say something about the heat transfer, or vice versa. So if we think about it, if we were to, for example, measure the heat transfer coefficient for some object in a flow, then we could say something about what the drag force was on that object in the flow. But there are a number of requirements that have to be met in order for us to make this analogy. And this analogy is specifically known as the Reynolds analogy. There are also other analogies. We haven't written the equations we haven't written the boundary equations for concentration in the flow. That's a mass transport problem that we're not dealing with in this class. But there's a very strong analogy between mass transport and thermal transport. But in order for these analogies like the Reynolds analogy to be valid, we have to be able to satisfy a certain number of requirements. And those requirements include the assumptions that go into deriving these equations, and one of those is that it's laminar. So this analogy is only going to be reasonably valid for laminar flow. Second one is what we assumed here in neglecting this pressure gradient term. So we need to have a pressure gradient term that's small. And finally, we really need to have a Prandtl number that's not too different than 1 for this Reynolds analogy to work. But under those conditions, which are frequently reasonably close to being satisfied, we have this extremely useful analogy that basically allows us to measure one physical quantity and say something about a very different physical quantity, but a very useful one.